Okay, so let's take a look then at user input validation using checksums. So we're going to look at some very commonly used checksums just to get a feel for how they work. Now, user input validation is typically carried out by the client using some client-side programming language. So JavaScript is often used for that. And that's one of the most useful things we can actually do with JavaScript, is we can use JavaScript to check to see if the data that someone put in looks okay. We need to see if it looks like the way it should. So the user might enter some data, and then the validator would check the format of that. And if it's not okay, it would say to the user, you did something wrong there, you need to fix that. And then only information that looks right will be sent on to the server for processing. So you can imagine if you're asking someone to sign up for a service and they have to give you their phone number, and someone says my phone number is 0875412. Well, you'd be looking at that and you'd be saying, I don't have to phone that to know that it's okay. I don't have to check any database to know if that's your actual number or not. It's just wrong because it's too short. Okay. So it can happen that when the user is inputting a long string of numbers, so a good example is a credit card number, that they can make a mistake. And we can look at that, and depending on how the information is organized, we can sometimes say, actually no, there's something wrong with that there too. So this can make for a better user experience because obviously they're not sending off data that's faulty. Also, because the validation can happen at the client side, it's typically very fast. It's also very efficient because we don't waste the server's time with data that we know is no good. Now, typically the input validation will involve a combination of work done by the browser on the client side and by the server on the PHP side. We've also seen that HTML5 actually provides some built-in validation for certain data types without writing any code at all. So between HTML5, JavaScript, and then PHP, we'll be checking the information, checking the input provided by the user at different places. And typically it's a combination of all three of those. Let's consider a very, very simple example, okay? So we know that a phone number in Ireland, a mobile phone number that is, starts with 0 and 8. And then after that you can have a 3, a 5, a 6, a 7 or a 9. I don't know if there's an 084, I'm not sure. And there used to be 088 a long time ago, but they're gone now. That was for the analog network. And then after that, it's 7 digits. So all mobile phone numbers in Ireland are 10 digits long. So if we asked on a website for an Irish mobile phone number and someone gave us, 8 digits, well, we'd know then straight away something was wrong. There'd be no point in, processing that any further, or trying to verify it or check it against a database of numbers, or even, compare it with the databases in our database, with the numbers in our database, and go looking for that entry in the database, because we know it's dodgy. We know it's bogus. We don't even have to look. So that's based on just the format of the number. And so we might have to write special code for that in JavaScript, or we might even use a regular expression in either JavaScript or indeed PHP that could check the format of the number. Using a checksum takes that sort of to the next level. So let's say it was a huge problem in Irish society of people giving out fake phone numbers. Okay, well, we could devise a system whereby we used the last digit of the phone number as a sort of a test. So we could make up a scheme, right? And this is just made up now, I just made this up. We could devise a scheme whereby the last digit of any phone number had to be equal to the number of even digits in the rest of the number. So if someone didn't know this rule and just made up a number off the top of their head, or typed in a number by accident, made a mistake, which is a more common occurrence, then we'd be able to detect that something was wrong. So if someone said their number was 08799966664, well, we'd look at that and we'd go, hang on, something's wrong, because for it to all add up, the last digit should be 5. And so we could tell then that something had gone wrong there. So maybe the number is actually meant to be, for example, 08799999664, for example. Okay, but anyway, we could look at it and we could tell that something is wrong. So when you have a checksum, the chances of a randomly generated number being accepted or a number typed in an error being accepted go way, way down. Now, of course, one of the disadvantages of using a checksum is that you're actually requiring more information than is necessary. So in this scenario, for example, this wouldn't work in Ireland because we would only have available to us 10% of the phone numbers. Instead of having so many millions of numbers, we'd have only 1/10 of that. So we'd probably end up having to use like 11-digit phone numbers if we were to introduce a checksum. Now, typically checksums aren't as simple as this. I mean, this is a very contrived one that's really, really very simple. Often the calculation is more complex and also can catch more kinds of errors. The most common error, for example, is transposition, where instead of doing 1, 2, 3, 4, 5 digits, you do 1, 2, 4, 3, 5. That you'd switch digits, switch the order of digits. And so we want to catch as many kinds of mistakes as we can. Now, the most popular checksum algorithm by far is the algorithm that is used to validate credit card numbers. So this is the Learn algorithm, and this has been around a very long time. So it turns out that the last digit of a credit card number isn't actually part of the number per se. It's there just to check that the rest of the digits were put in correctly. No, it can't tell you if the card is stolen or not. It can't tell you if the person has any money or not. But you may have noticed that when you're entering a number on a website, if you make a mistake, the website very, very quickly tells you that you made a mistake. Very often you don't even have to click submit. As you're typing, and when you leave the field, it goes, there's an issue there, and it might highlight it. And that's because it uses this algorithm to check to see if the number looks legitimate. Okay, and the algorithm is like this. So, starting with the second last digit of the number, we multiply every second digit by 2. Then we add the resulting digits together with the unmodified digits and the checksum. And when we add all these up, the total should be evenly divisible by 10. If it's evenly divisible by 10, yip-de-doo, the number is legitimate. If it's not evenly divisible by 10, there's an issue. There's a bit of a little programming hack you can do actually when you're adding up the digits that result from the multiplying by 2. Separating out the first digit and the second digit and then adding them together can be tricky, but actually in this scenario, if the number is greater than 9 and less than 19, then actually subtracting 9 off it, does the job anyway, and that's easier, a little bit easier to code. So if we look here, we can see that here's a number I made up. So we multiply every second digit. So here we're doing 2 then 7, then 0, then 8, then so starting at the back now, okay? And as a rule, if you forget how this works, you never modify the checksum digit actually. That always stays intact. So even if you know it's every second one but you're not sure which, we know that the checksum itself doesn't get modified. So starting at the back, and the reason we start at the back is because there are actually some credit card numbers that might not be length 16. If you were certain it was a 16-digit number, you could start at the front and work your way forward. But we describe the algorithm as starting at the back just to make sure that we don't ever, kind of like it's odd, even, we make sure we get the right one. So starting at the back, we don't multiply, don't multiply, don't multiply, don't multiply, and so on like that. So 2 is left intact. 2 multiplied by 2 is 4. 4 is left on its own. 7 multiplied by 2 is 14. That 14, when you add the 1 and the 4 together, becomes 5. So it contributes 5 to the total. 1, we don't do anything. 0 multiplied by 2 is 0. 8, we don't do anything. 0, we don't do anything. 0 we multiply by 2, which is 0. 3, we don't do anything. 8 multiplied by 2 is 16. 1 plus 6 is 7, so that contributes 7 to the total. Next up is 2. And then 2 times 2 is 4. 9. 9 times 2 is 18. 1 plus 8 is 9. Then we have 4, and then we have 4 again, which times 2 is 8. And when we add up all these values, 8 plus 4 plus 9 plus 9 plus 4 plus 2 plus 7 and so on, it turns out to be 70. And 70 is evenly divisible by 10, so yip-de-doo, this number is good to go. The beauty of this checksum is that it's really quite simple, it's not that complicated, and it's very good at catching the number one error that people make, which is transposing digits. So if I did 44992238 instead of 83, well then the 3 would have got multiplied by 2 instead of the 8, and the total wouldn't have worked out to be evenly divisible by 10. Now it does mean, of course, that we're sort of wasting a digit on the checksum, but you can see that it is very useful. As it turns out, Visa cards always start with a 4, and they can be length 13, although I haven't seen any of those in Ireland, or length 16. American Express starts with 3, 4, or 3, 7, and they're length 15. So because we can have odd and even lengths, that's why we start at the back, just to make sure we get it right. MasterCard ranges from 51 to 55, that's length 16, and then Discover Card, which you don't see in Ireland at all, I don't think, begins with 6011, that's length 16. Now you'll see the learn formula used all over the shop. You'll probably find it's used on your supermarket loyalty card, anything like that really, and it's a very handy way of checking for errors. A randomly generated number, if you think about it, will have a 1 in 10 chance of getting through the test. So it'll catch 90% of randomly generated numbers, which is fairly impressive. Now, the next checksum we're going to look at is kind of a variation of the learn formula, and this is the International Article Number, which used to be known as the European Article Number, so we still abbreviate it actually with EAN. And this was a European scheme that was then adopted in other parts of the world too. And this is the barcode that you see on products. So EAN 13 is the barcode you see on your Coca-Cola or on your packet of crisps, whatever the case may be. And in this scenario, the last digit is the check digit. And this looks a lot like the Lun equation, except we multiply by 3 for every second digit. So it's great again at capturing transcribed digits. And we don't bother with this business of adding the digits together. That's an unnecessary complication. So here, a 7 will get, we're starting at the back again, starting at the end. 7 will get multiplied by 1, which will give us 7. 5 gets multiplied by 3, which gives us 15. 4 times 1, 3 times 3, giving us 9. 2 times 1, 1 times 3. So every second digit gets multiplied by 3. We add them all up together, and then at the end, the answer should be evenly divisible by 10. So you can see this is very like the one used for credit cards, the Lund formula. The International Standard Book Number, or ISBN number, is an interesting one. And there are actually two variations of this. The original ISBN number was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 digit number. Okay. And the last digit was the checksum, as you'd expect. Now this was interesting because the multiplication was more complicated than the previous two. So in this scenario, the checksum is untouched. It gets multiplied by 5. The second digit from the end gets multiplied by 2. The third from the end gets multiplied by 3. The fourth from the end gets multiplied by 4, and so on. So we're multiplying by 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. You can see how programming lecturers love this example, because you have like a loop and you have counters and all this kind of thing. It's great fun. Now, looking at this particular example here, we can see that 5 times 1 is 5, 2 times 2 is 4, 6 times 3 is 18, 1 times 4 is 4, 5 times 5 is 25, 9 times 6 is 54, 7 times 7 is 49, 8 times 8 is 64, 7 times 9 is 63, and then 0 times 10 is 0. We add them all up, okay, and then we do a mod 11. We see is it evenly divisible by 11. So in the previous ones it was 10, here this is 11, okay, and we see that 11 is a special number. We'll see that in a second. And so if it's evenly divisible by 11, we're good to go. If it's not evenly divisible by 11, there was a problem. Now, when you're calculating the checksum, I mean, what you have to do is you have to do the multiply by 2, by 3, by 4, by 5, by 6, by 7, by 8, by 9, 10, see what you get, and then figure out what you need to use for the last digit, use for the check digit, to bring you up to a number that's evenly divisible by 11. So that could result in a scenario where you want the last digit to be 10, but of course we don't have a digit 10. Do you know what I mean? We have a 1 and a 0. That would add an extra digit to the number. That's no good to us. So in the scenarios where you need it to be 10, you use an X, and that comes from the Roman symbol for 10. So you'll notice if you go to Amazon and you look at a book that's old enough, okay, some books only have ISBN 13s, we'll see in a second, but if you look at a book that's old enough, you might find that the last digit of the ISBN number is X, and that X is for 10. So if it's X, you multiply 10 by 1. So the last digit can be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or X for 10. We no longer use ISBN 10 for new books, okay? So new books are issued with ISBN 13 numbers, right? And ISBN 13 is actually just an EAN 13, but the 3 digits that would be used to specify the country of origin of the product are 978 or 979, and we call those Bookland. So if you want, you could go look at Amazon and find some books with ISBN 10s, see how they're good, and then generate ISBN 13s for them and see how they look. Obviously the check, it's not just a matter of slapping 978 in front of it. I mean, you need to recalculate the checksum, obviously. In general, when we're looking at checksums, they often have some common features. The modulus that you choose is typically going to be greater than the number of digits. So you notice that the ISBN was 10 digits long, and so we did mod 11. And the modulus also needs to be greater than the range of any single digit. So prime numbers work especially well, and we do see prime numbers coming up a lot when we're looking at check digits. In your bog standard ISBN 10, errors have a 90% chance of being caught. 10 in every 11 made up numbers would be caught. In EAN, we're talking, I guess, we're talking about 9 in every 10 random numbers being caught. Now, a very interesting and somewhat complex check digit system is used in Irish PPS numbers. So every person working in Ireland has a PPS number, and children who are born in Ireland get issued them at birth. If you're not born in Ireland, you will be issued the number when you move to Ireland permanently or semi-permanently, or if you start working in Ireland, or if you go to school in Ireland, you'll need one. Actually, from a data protection point of view, they're quite regulated, and the number of organisations that can request them and store them is very specifically controlled. So, the police can only ask you for your PPS number if they want to give you a job. It's in contrast with, say, the fairly relaxed approach Americans have to their social security numbers. So the plain vanilla PPS number is 7 digits followed by a letter, a checksum letter, okay? And we'll have a look at how that works. So we multiply the first digit of the PPS number by 8. The next digit gets multiplied by 7. The next one gets multiplied by 6. The next one by 5, and then by 4, and by 3, and by 2. As is common, we leave the value, whatever it would be, at the end, the checksum. We don't multiply that by anything or alter that typically. We add up all of the sums of our multiplications. We add up all the multiplications, we sum them all up, and we get a total. Okay? So in this case, the total is 169. And so we do 169 mod 23. So modulus is, the remainder after division. So if you divide 169 by 23, you get whatever remainder 8. And then that value maps to a letter. So in this case, the letters are fairly organized. So it's A, B, C, D, E, F, G, as you would expect. And 8 gives us the letter H. So the correct letter for this PPS number then is H. So if you present to a government system 6059922P, for example, it will calculate that the number should be H. So that number would give rise to a checksum of H, and if you're saying it's P, well then something is wrong. So if you were to randomly make up a PPS number, you would only have a 1 in 23 chance of being right. Okay, so that's pretty good odds from a validation point of view. If the number is evenly divisible by 23, then the mod would be 0, and that results in the last letter, the check letter, being W. So if you're programming this up, that's kind of an exception you just have to check for. Otherwise, it's quite regular, because if you're writing code for this, because it's so regular, A, B, C, D, E, F, G, it's not like you'd say, if it's 1, then A, else if it's 2, then it's B, else if it's 3, then it's C, else if it's 4, then it's D. You wouldn't even have to do that, because you could map, the modulus, offset that into a string, or use the ASCII values or something. There'll be a hack there that would mean you wouldn't need 23 ifs, but you would probably need an if to check if it's 0. Just as a sort of an aside, as an anomaly, you would see on forms in the past, there would be the 7 numbers and then a space for 2 letters. And in the past, women were issued PPS numbers that were identical to their husbands, but with a W at the end. And the W was for wife. Now, that's really just an historical thing. Pretty much all of the women that would have had such numbers have now been migrated and have been given PPS numbers of their own, because women are people in their own right and not just extensions of their husbands. So, but in the past you would have had that system, and so the W wasn't a check letter there, it was just W for wife, but that practice has been discontinued. Now if you look there, if you have how many digits? 7 digits. That gives you the possibility of having 10 million unique numbers. Given that the population of Ireland is about 4 million-ish, you could see how, if you don't want to reuse the PPS numbers of dead people, that starts to become a problem, because you can only have 10 million in total. So eventually we would run out of PPS numbers. So a new system was introduced in 2013 where there was an extra digit, an extra letter applied, and they designed the system so that it was backwards compatible with the old one. So in the new system there's 2 letters, okay? But the second letter is just used to calculate a value that's added into the total. So the second letter contributes something to the total, and then the checksum letter is calculated as before. So this now would give us then, if we have 26 letters, that would give us 26 times the number of possible unique numbers, which should keep us going for a long time, really. So anyone who was born after 2013, or anyone including 2013, and anyone who moved to Ireland after 2013 would have one of these letters, one of these PPS numbers with the 2 letters, and typically they have the just the A. I'm not sure, but I haven't seen anything other than A as the second letter, and in 10 million more people we might move to B, so we will be A for quite some time, I think. So just to look at how that works, it seems very complicated, but it is not really, because all that happens is that the letter is given a value equivalent to its position in the alphabet. So A would be 1, B would be 2, C would be 3, and so on. And then that gets multiplied by 9, which, if you think about it, is the multiplier we haven't used yet. And then that just gets added into the total. So in this scenario, like 8 plus 14 plus 18 plus 20 plus 20 plus 18 plus 14 plus 9 would give us 121. And then, as before, we do the mod 23, which would give us 6. And then 6 gives us F. So then the check letter becomes F. The great thing is that if you consider the absence of the second letter to be equivalent to a value of 0, well then you can do 0 multiplied by 9 isn't going to add anything to the total, and so the old numbers would be giving the correct result using the same calculation. So that's kind of handy. So you can write this code then for new and old. You don't have to do like, if it's an old number to this, if it's a new number to this, the calculation will be the same in both cases. Now, although the Irish one is perhaps one of the more elegant and one of the more complex ones, I want to look here now at another one from Finland, which illustrates some other points you might want to consider if you're designing such a scheme. Okay? And so Finland has two official languages, Finnish and Swedish. I can pronounce neither, so I'm not going to attempt any of these. But in this system, okay, the first 6 digits of your ID number are your date of birth. So if you were born on the 10th of May 1980, you would get 100580, for example. Now, you do have the issue of, by using only 2 digits for the year, you have a sort of a Y2K type scenario where people from different centuries then might have the same number. So there's a separator between the date of birth and the rest of the number. And if you're born in the 1800s, that's going to be plus. If you're born in the 1900s, that's going to be minus. And if you're born in this century, it's an A. Okay? So what's happening there then is you're managing to code the date of birth completely, but you're only using 7 digits instead of 8. I mean, it's not a big deal, I guess. Now, following then is 3 digits, and that's a number that's unique to all the people born on that day. So they're given out one by one, and if you're born on that day, you'll have 3 digits to separate you from the other people. Interestingly, they have decided to code in the number not just the date of birth, but also the sex of the individual. So if you were female, you will be given an even number, and if you're male, you'll get an odd number. This system is quite limiting, of course, because if you think about it, it means you can only have like 500 men born on any given day in Finland without the system collapsing. But, you know, that's actually not a big deal for Finland. The birth rate in Finland and the population is such that really there's kind of less than 100 a day. So it's not going to be a problem for Finland anytime soon. And then the last digit is a checksum. And that character can be a number or a letter, okay? And it's basically selected from those letters and numbers you see there. And so if mod 31, for example, turns out to be 15, then you'll get the 15th character there. Looking at it more closely, right, you can see that it goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, fair enough. And then it goes A, B, C, D, E, F. Look, there's no G. Then you've got H. There's no I. J, K, L, M, N. There's no O. And what else is missing? The Q is missing. And why do you think that might be? Well, remember, the purpose of having a system with a checksum is to avoid errors, to avoid data entry errors, to avoid people putting in the wrong values. And if you think about it, it's something that might have been considered in the Irish system perhaps, although Ireland only uses letters. But you can see how the letter O can very easily be mistaken for the digit 0. I mean, even in Ireland, when we call out our phone number, we always say 087. We don't always say 087. But of course, in a computer system, the big difference between 0 and O. Similarly, G could quite easily be mistaken for C, and Q could be mistaken for 0 also. So because they only needed 31 values, they chose the 31 quite carefully in Finland to minimize the possibility of errors. I actually think U and V were good candidates for being confused as well, but I guess if you removed V in favor of U, you would then have to contend with Z, which can be very easily confused for 2 if poorly written. So I thought that was a very interesting and very clever choice they made in Finland, rather than just using the first 21 letters of the alphabet. So anyway, if we look then how it works out, so a person born on the 31st of December 1980, I guess, if they got 999, which we've seen actually would be quite unusual. So the digits, so we ignore the separator, the digits then are treated as basically a large integer, and we do a mod 31 of that to give us 17. So you see that in Finland they didn't bother messing around now with multiplying by 9, by 8, by 7, by 6, by 4, by 3 and by 2. Didn't go in for any of that. Just the number part is a big number, we do mod 31 and we get the remainder. And so the 17th character of that string, no, they did what a computer programmer would do. The 0 is the 0th character of the string. So there's 31 characters. The first one is 0, the last one is 30. The 17th character of that string is J, so the Czech letter for this particular number is also J. So it does turn out that people who were born on the same day in different centuries could potentially have the same Czech letter. No, we don't have to go quite so far north for our next checksum. What we're going to look at here is the serial number on euro banknotes. Now these are what I would call the old notes, actually. You don't see many of these about anymore, certainly not in 5s and 10s, but you do see them in the hundreds, alright, and you still see some old 50s. So with this serial number, the first letter actually represents the country where the note was printed. Originally there was a great plan where they would be sort of in alphabetical order, but someone discovered that unfortunately the letter had been assigned to Greece. It wasn't actually in the Greek alphabet, so they did a bit of a swap. But anyway, so you take the first letter and you convert that to a number, where A is 1, B is 2, C is 3. Each country has a slot, actually, even the ones that aren't in the EU yet, and even some that are leaving. But anyway, so that becomes a number, and then you just add up all the digits, okay, after that. So in this example here, which I pulled out of my wallet a few years ago, it all adds up to 71. You add all those digits together as often as is required, and eventually you will get 8. Okay, so that's how you do it in the pub. You'd add the digits together. As it happens, there's sort of a programming hack you can do where when you're adding digits together like that as often as required, doing a mod 9 will have the same effect. So that's much easier to program. I asked a maths person once, like, was that always true, or was I just imagining it? And he came back with a big long answer, which I think was yes, but I didn't understand the answer. But anyway, this seems to work where you can do a mod 9 instead. So basically, add up all the digits, do a mod 9, and you should get 8 as your answer. If it's not 8, then somebody has made up the serial number. Obviously, you would think if someone was going to the trouble of forging banknotes, they would at least come up with decent serial numbers. But it is useful there. It's just a checksum one. What's handy about this one is if you have some of those notes, you don't have to go looking far for examples. The newer notes, the New Europa series, uses a different numbering system, okay? And we'll take a look at that. So in this scenario, this is a number I pulled out of my wallet. It starts with 2 letters again, instead of 1, but this is not the country code, okay? The first letter turns out to be the printer, and what we do here is we assign the number associated with that letter. So T, A is 1, B is 2 again, and so T would be 20 there. The next letter then we can do by assigning the number associated with that. In this case, A is 11, B is 12, C is 13. You could, in fairness, from a programming point of view, use the same piece of code that you used for this one here, and then just add 10 to it. Do you know what I mean? You don't have to write new code for that. But this is just the way the algorithm was expressed when I found it. And then you basically take the remainder of the number as a big integer, and you add the values from the letters to it. And this will give you a big, huge number. You do a mod 9, and if it's equal to 8, then it's good to go. So in terms of coding that, you probably write the code slightly differently. You would modify the algorithm just to make it easier to code from what I've explained here. It's more complicated than it needs to be. So next up, we're going to look at the PESEL number. This is the ID number that Polish people have. So it's like a PPS number for Polish people. I won't insult any Polish speakers by having a lash there at the pronunciation. And not unlike the Finnish number, the Polish number encodes the date of birth of the owner of the number into the number. So the first 2 digits are the year they were born, the next 2 digits are the month, and then the next 2 digits are the day. Okay? Then there is a number that's issued individually, and then the final digit is a checksum. We'll look at the checksum in a minute, but you notice here that unlike the Finnish number, there isn't a separator that would distinguish between people born in different centuries. However, the Polish civil servant that was responsible for this scheme came up with a great plan, because of course if you're using 2 digits for the month, right, that's fine, but of course the month is only ever going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 or 12, but you actually have space in the numbering system for like 99 months. So quite cleverly, someone in Poland decided that if someone was born in this century, as opposed to the 20th century, you would add 20 to the month. So this turns out to be a quite clever way of encoding some extra information without requiring an additional digit. So if someone's year is 70, but the month is 25, well, if we subtract 20 from 25, we'll get 5. So this is telling us that the person was born in May 2070. So this is quite a clever little scheme, and that's going to see Poland good to go for a couple of 100 years, about 500 years more. So this should be fine. The checksum calculation is reasonably straightforward, and this should look familiar. So this is in essence the same scheme used for the, well, no, it's not. I was going to say it's the same as the EAN because it's 13131, but no, it's much more complicated than that. We can see there, look, we do 1379, 1379, 131. The one at the end, of course, because we never multiply the checksum itself by anything. So it's doing 1379, 1379, 1379, except it stops. So this is going to be a very good way of catching digits that have been transposed. You add them all up, and it's evenly divisible by 10, then yip-de-doo, you're good to go. Now, we've had one from the west, one from the north, one from the east, so it's time to head south. So, Spanish ID numbers are 8 digits followed by a Czech letter. And the calculation for this is simple enough, really. We treat the numeric part as a big, huge integer, and we do mod 23 of that. So that mod 23 can result in possible values of 0 up to 22. And then what we do is we look up the letter that goes with that number in a table here. So unlike, say, the Irish scheme where A is 1, B is 2, C is 3, D is E, and there's some sort of logic to it, this seems to be somewhat random. You notice that sensibly there is no O and there is no I among the letters, so they have been chosen to minimize possible confusion, so that's good. But the order of them seems to be random. I've asked many Spanish computer scientists, and actually know quite a few of them, and they can't tell me, there doesn't seem to be any logic or reason to the particular choices here. So maybe just someone just made them up. That X is 10, which is the Roman for 10, suggests that it's just random. Okay. Sometimes people use a dash to separate the number from the letter. So if you're accepting input of a Spanish ID number, a DNE, you would be expected to organize it so that if they put in a dash, it's not going to break it. So let's have a look here. So if we have, if your ID number was 1, 2, 3, 4, 5, 6, 7, 8, well, what letter then would be the Czech letter associated with that? Well, 1, 2, 3, 4, 5, 6, 7, 8, mod 23 is 14, and the letter that goes with 14 is Z. So your number would be 1, 2, 3, 4, 5, 6, 7, 8, Z. Or you might write it 1, 2, 3, 4, 5, 6, 7, 8 dash Z. So that's something to watch for there. If you haven't had enough trivia for the day, if you're Spanish, you'll recognize all of these characters. It turns out that General Franco assigned 0000001 to himself, and basically the first 100 numbers were reserved numbers, and so Juan Carlos, the king, the former king of Spain, he was number 10, and 11 I think was his wife, Reina Sofia. The current king, Felipe VI, is number 15, and so on. Unlike Ireland, where people are very, very strict with their PPS number and who they would give it to, in Spain you're frequently asked for your ID number. Even if you're just buying a bus ticket online, they'll want your ID number. So if you don't have one, or you don't feel like giving yours, perhaps you can use the king's one. So what then would the Czech letter be for Juan Carlos? Well, 10 mod 23 is 10, so he would be 0000010X. If you want to pose as the current king of Spain, 15 mod 23 is 15, so he would be 0000015S. I'm not sure if you'll get into trouble for impersonating the king, but sure, you can give it a lash. I remember reading somewhere that actually someone forgot to hard code into the system that the first 100 digits were reserved for special people, and the system actually rolled over and wrapped around, and so in some village somewhere in Spain there is some pleb who has the same ID number as the king. I'm sure the scope for confusion is quite limited. Let's take a look next at France. So in France you would have a couple of different numbers, but one of the numbers would be the one issued by the Institut National des Statistiques et des Études Économiques. So that's some sort of statistics office. And this is quite a long number. And there's various bits of information encoded in this actually. So the first digit is for the sex of the individual. So you'll get 1 if you're male and 2 if you're female. So unlike, say, Finland, where the sex was encoded in a single digit by being odd or even, in France they're using 1 or 2. They're using a whole digit for that. That's actually a very interesting one, because it does seem very wasteful, doesn't it? If you could just use the fact that someone has an odd or even value, you could encode the sex in the number if that was something you wanted to do, without wasting a whole digit on it. The story behind this is actually quite interesting, and I leave you to Google that to figure out whether the French were being just inefficient or whether there was something else going on here. But it's certainly a sign that history casts a very long shadow and things remain in the system for a long time. No. So the next 2 digits are the year of the birth, and then the next 2 digits are the month of your birth. And then it doesn't bother so much with the date. The next 5 digits are the place where you were born. So if you know about France, you know that every département has a number, and there was a time these are on number plates, and you could have great fun seeing where cars were from based on the number. So 22 is Côte d'Armor, which a lot of Irish people would be familiar with because it's in Brittany, and so 22 is that department, and then the remaining part of the number would be the actual place in that department. So in essence, this is your postcode. So the postcode of the place you were born would be encoded in your number. So you can imagine that's quite specific. It turns out if you're not born in France, you'll get a 99, and then a code representing the country. The first digit of that will be the continent you were born on, and then the country. So if you were born in Ireland, for example, and you moved to France, you'd get one of these numbers. So it would have the first digit for your sex, then the year you were born, the month you were born, and then because you're born in Ireland, you'd get 99136, as it happens. Then there's 3 digits which would be assigned to each person. No, so that only allows for 1,000 men and 1,000 women in each department, but of course departments can be quite small. And then finally there is checksum, and that's a 2-digit checksum. So the French didn't want to be outdone. 2 digits, and you treat the numeric part as a big number, and then you add to that the checksum, and at the end of it all you get a big number, and that number must be evenly divisible by 97. If it's not evenly divisible by 97, there's a problem. So you can get various examples of these. The People's Republic of China uses a mod 11 checksum. The number you get in the UK has a checksum calculation. In Italy, there's quite a lot of information encoded in that. There's the place your mother was born, things like that. IBAN bank numbers, they're an important one. There's a checksum there. Many barcodes have checksums too. Different countries have different attitudes to ID numbers. If I'm not mistaken, there's no single numbering system in Germany. Germans are quite paranoid about data collection on individuals for historical reasons. So it varies from country to country. So with all of those examples, then you can see that they have quite a lot in common. Sometimes we like to, if we multiply numbers in the checksum by some multiplier, then it's very good at catching transposed digits. Some people like to keep it simple and just treat all the digits as a big number and do a mod. And the mods are almost always of prime numbers, and that's just to do with the maths and the way these things work out. So if you were designing a system where people were going to have an ID number, like a membership number, a library card system or whatever, you could encode some sort of checksum into the number, and then that would help you catch any mistakes or any data entry errors, or even someone just trying it on.